Okay. So 7:30 and the exam corrections were due before class today. Fortunately, only 25 submissions. So I'm guessing all of you guys can show up. Doing these, I guess for the people that are watching the recording, if you did not do your exam corrections and you did not do well on the exam, I would suggest that you try and make sure that you understand the single cycle data path, pipeline data path, and then performance for those. Because going forward, you're going to need to understand these things. Even though the exams are not cumulative, you need some prerequisite knowledge in order to understand the needle. Alright, so for today, we are doing exceptions and interruptions. So these are kind of unexpected events that change the normal flow of the instruction execution. They're unexpected in that we don't know when they will occur, but they are still expected because we need to know how to handle them. So things that can give you these exceptions or interrupts are, for interrupts, it's external input outputs. So like me moving the mouse around. This is an interrupt. It does stop the execution of the current program so that it can then process what this input is. The reason that it seems instantaneous is just because it switches very fast, right? And then exceptions. These are arising within the CPU. So this happens when you have some bad instruction. Maybe it is undefined opcode, or there's some overflow flag, or you're trying to reference memory that you're not allowed to reference beyond, right? Because every program has like this sliver of memory that they're given by the operating system. If it tries to access memory that is belonging to a different program, we're going to have some exception, and the operating system is going to say, no, you can't do that. And it will then handle that exception, kill the program maybe, or it will correct the error and then the program can resume. So like if it is killing the program, seg faults, right? That's it killing the program. All right, so dealing with them without sacrificing performance is very difficult. So we're going to talk about detecting and taking appropriate actions and how it's often on the critical path for our data path. So for handling exception in MIPS, exceptions are managed by a system control coprocessor. And it's going to save the address of the offending or interrupted instruction into this exception program counter. Okay, so this is the address of the instruction where the interruption or the exception occurred, right? So if this is maybe a load word trying to access data beyond its memory, then that load word instruction would not finish executing, and we would save the program counter of it so that we can resume if the handler of the exception or interrupt decides that the program can restart and the error was fixed. So the other thing that the handler is going to need beyond the program counter to be able to recover is what is the cause? Okay. So we have this cause register. For now, let's just assume that it's 1 bit. If it's 0, that means that it was an undefined opcode, so bad instruction. If it's 1, that means there was some overflow. Right? But in reality, there's many different other types of these exceptions. And we're also just going to imagine that we're going to jump to exception handler at this address in memory. So the exception handler would be in some address in memory that the operating system would be under control of, but it might not exactly be this address, right? Just using it as an example. So alternatively, we can have these vectored interrupts. So rather than just having one handler for all these different kinds of interrupts or exceptions, this vectored interrupts means that based on the exception or the interrupt, there's a different handler that would work on that problem. So like, if it's an undefined opcode, rather than just jumping to one place, being 8,000 and then 180, we would jump to C0 if there's an undefined opcode. But if it's overflow, we're going to jump to this handle. Okay. And for all of our different kinds of exceptions and interrupts. So what these handlers are going to do, it's either going to deal with the interrupt and maybe resume execution, or it can jump to a different handler. And maybe that handler will be the process that kills the original process, if that is the case. But in order to decide what to do, it's basically going to do these things, right? It's going to read the cause. So if we don't have this vectored interrupt, we don't automatically know what the cause is, right? But even then, we might want to save, like, was it overflow or was it underflow, right? So we're going to read the cause, and then based on that, we'll transfer to a relevant handler. And then that handler will determine what is the action that is required. And if it's restartable, it will take that corrective action, and then it will use that program counter that we saved to resume the program. Otherwise, if it's not restartable, it's just going to terminate the program, and then using the program counter, it can say, this was the instruction that caused the error, this was the error, and so forth. Right? So you can kind of give the user some hints as to what happened. So this is our pipeline data path. Right? This has everything that we have talked about. We have moved the branch instruction to decode stage as a last class, right? And before that, we added these forwarding units, hazard detection unit. And now what we're adding is, here's our address of the handler, right? So we can change PC to that based on if we have some exception or interrupt. And then over here, we have in the execute stage, because that is where we're first doing anything, right? This is where we would see, is there overflow? And also, this is where anything would change, like before anything would change. So if we have a bad opcode, it can go into this next stage, and then we can say, okay, we're not going to let it go forward now, right? So we have these two registers. What is the cause of the exception or the interrupt? And this is my resuming program counter. Right? So then once we have this, the handler takes over, right? All of these instructions behind get flushed. And then the handler will start to execute. So if it's just a simple interrupt like the mouse movement, right? The handler will just get that mouse movement data, have the operating system process it, and then it can very easily return to the program with this error program count. But if it's a out of bounds memory address, maybe the handler decides we can't fix this. You are not supposed to be accessing this part of memory. I'm going to kill this program. And I'm going to print out to the console or whatever. Program killed at this address because memory out of bounds, right? Okay. So for the restartable exceptions, we are going to flush the offending instruction and all of the instructions after it. But the instructions that are before it, we don't need to flush those, right? They didn't have an exception, and the exception didn't occur until after they were already being finished executing. So once we do that, the handler is going to execute and then return to the instruction where the exception occurred. And it's going to refetch and execute from scratch. So all of those instructions that were after it, we are going to refetch and redo as well. And we can do this because we have the PC saved in EPC, right? And one thing to remember is that we actually save PC plus 4 because in the instruction fetch stage, we are always incrementing PC by 4. So this is just something that the handler will adjust. So here is an exception example. We have this code. We execute the subtract, then an and, then this or, and then say this add has some error that it throws. Maybe it's overflow, something like that. What's going to happen? Right? Here's our and, here's the or, right? This is our exception. So what happens to the and the or? They just finish executing it. So we don't do anything. What happens to the add? It is stopped, and we do this by we're going to flush it, and we're going to save
The program counter in lazy.
the cause and the program counter that doesn't really point to this add, but it points to this set, right? Because we have PC plus 4 over here. What happens to the set less than?
Did a restartable exception or?
Either way, the same thing is going to happen first. We flush this, right? What happens to this one?
Flush it all.
Yeah, we flush this, and like you just mentioned, we flush all of them behind. So we're going to flush the load word too. Because if it is restartable, we'll start fetching from the add. So then we'll fetch the set less than, we'll fetch the load. So next cycle, right? We let that and finish. The or continues to finish too. Our add became a bubble, and set less than load word also became no ops, right? And we started fetching from our handler. So one thing that can occur is What if there's multiple exceptions? So because of the pipelining and overlapping multiple instructions, we can have multiple exceptions at once. So the simplest approach is just deal with the exception from the earliest instruction, right? So we're just going to flush that other exception that occurred. And if we are restartable and we fix the first exception, the second exception will then occur again when it is executed, and then we'll fix that, right? But as we talked about, this pipeline that we have and data path we have looked at is very simple, right? Or easily, it's supposed to be easy to understand and introductory to the topic, right? This is just introduction to the data. But we have talked about how there are more complex pipelines. Okay? So one of those types is you can fetch multiple instructions per cycle. And if you're fetching multiple instructions per cycle, if you want to execute multiple instructions per cycle in each stage as well, right? Otherwise, you're just fetching and you're never going to keep up with it. So in this case, maybe we can have two instructions that have exceptions at the exact same time. And they're in the same stage. So again, you can just deal with this simple approach. Just deal with one of them first. And then deal with the next one next time. But if you have out of order execution, then maintaining these precise exceptions is very difficult. Because now I have to keep track of when was this instruction actually supposed to finish? What was ahead of it? What was behind it? And recovering all of that, making sure you flush the correct instructions becomes more difficult. And it's because of this that this exception and interrupt is often on critical path, because this is very complex to figure out in hardware. All right, so we're going to take a look at the final data path. Right, we had started with single cycle. We built each stage one by one, right? Then we graduated to the pipeline architecture, where we split up the single cycle data path into these 5 distinct stages. And we added forwarding, added hazard detection in order to stall if we needed to stall. And we added branching to the pipeline and moved it up from being handled in the memory stage to the decode stage to save us 2 cycles of stalling if we did need to stall. And now we've added exception handling. So this is our final pipeline data path with all of our components, all of our multiplexers. And here we can see our branch logic to detect if they're equal or not. We moved this adder that calculates our branch target address from the execute stage up here all the way to decode over here. So this is something that you should know very well, right? And I guess one other thing that is a smaller error that was occurring on the homework and the exams is just read the question carefully. If the question is asking you for the inputs into the register file, it's asking you for the register number, right? Not the data inside the register. If it's asking you for the outputs of the register file, it's not asking you for the register number. It's asking you for the register data. Okay. Same thing for if it's asking for inputs or outputs of like the ALU. So if it's that saying, what is the first input to the ALU? We're not asking, is it RS or RT? We're asking, what is the data, right? And then same thing for all of these muxes. If it's asking for the control value, that is our 0 or 1, or not for this case, but it would be for this one, right? The 0 or 1. Is it the data from memory, or is it the data from the ALU executes? Right, but if it's asking for the output, is it asking for that 0 or 1? No. It's asking for the data that it's selecting. Okay. Same thing for the input. Because even though we are, say, selecting from the ALU output because we're an add, there's still something that's going into this mux. So there still is this other input. And maybe it is X because for our type instruction, because we know that we're going to select this part of the mux. We don't care if we're reading from memory, right? So this mem read would be X. So then this read data becomes X2, right? So you would need to know that's the inputs to this mux. On this input is X. Okay. Just be familiar with this data path. I know it looks like a lot, but we have spent a couple months building up to this. Okay. So this is your question for today. Here. Your code is 194. We are past the threshold. So what are we saving for an exception? Do we save the PC address? Why do we save the PC address? To restart, if we can restart. Yeah.
And that counts as PC address +4.
And then do we save the cause of the exception?
Yes.
Why do we save the cause of the exception?
So we can tell the user what went wrong.
Yeah, if we kill the program, we want to be able to say what the cause was, but also when we're in the handler, we need to know what is the problem. Right? The handler either will be directly referenced based on the cause of the exception, or there's this overall handler that will read the cause and then jump to a different handler that will handle that specific exception. And then see program cycle number when the exception was thrown. Is this even helpful? Yeah, because this is going to be different every single time you run the code, unless you have no cache access, things like that. No other interruptions, right? So this is D, right? A and B. All right. So just as a preview for your presentations, I'm going to talk a little bit about some of the topics. All right. In computer architecture, we like to take advantage of instruction level parallelism. So it is something that we are doing in pipelining. We are executing multiple instructions at the same time, right? And we can increase this amount of parallelism by taking advantage of instruction level parallelism by having deeper pipelines, right? So less work per stage, shorter clock cycle, more instructions in flight at the same time. This is called super pipelining. This deeper pipeline. There's also multiple issue. So rather than just fetching one instruction and executing one instruction at each pause edge clock, we can fetch two instructions, decode two instructions, execute two instructions, and we can have basically a duplicate of our pipeline. And then when we fetch the two instructions, we can see, are they the independent instructions? If yes, then they can both be decoded together. And then they can be executed together and keep going together. If they're dependent, maybe they can still both be decoded together in our simple pipeline, right? But maybe one will go to executes and then the other one has to wait, right? And this multiple issue is not just for two instructions at a time. You can do 4 instructions at a time, 8 instructions at a time. In reality, most CPUs have at most done 8 instructions per clock cycle because you're just not finding these independent instructions, as well as your hazard detection and forwarding grows exponentially with the number of instructions that you're fetching, right? Because you can have these dependencies across all of these instructions. And the other thing is, because of this, we no longer are looking at CPI, right? Cycles per instruction. Because we're fetching more than one instruction and executing more than one instruction, we start looking at our performance equation in terms of how many instructions per cycle can we do. So an example of this is like if you have a 4 gigahertz processor with 4-way multiple issue, it has a peak CPI of 0.25, but peak IPC of 4, right? Did I fetch 4 instructions? I do 4 instructions. But again, these dependencies are going to reduce this in practice. So we already talked about this a little bit. So super pipelining, right? 5-stage pipeline. It's simple. It's a good start, but like I talked about, in reality, processors are having 20 to 30 stages. But even these ones, Pentium, super old processor. And now going into these deeper pipelines is going to let the processor clock run faster, right? Because we have our longest stage indicates our cycle time. So if we split up the pipeline more and more and more, our longest stage is shorter and shorter and shorter. And then once we get to a point, pipeline register overheads, because you have to have that clock to queue, and it's going to have your timing equation. Maybe the pipeline register is taking 50, 60% of the overall cycle time. Okay. And the other thing is we cannot just increase clock rates to infinity. We do have this thermal and power wall. We can't just have the processor go beyond around 90 to 100 degrees Celsius. And with the cooling capabilities, we have this wall that we are going to hit. All right. The other thing with the multiple issue pipelines is you can do static multiple issue, where the compiler is going to group instructions that can go together and package them into these issue slots. And the compiler is going to detect and avoid hazards. So if it can't find 4 independent instructions that can go into a packet, then maybe it just puts 3, and then the 4th one is a no operation. This is not typically done. What is typically done is dynamic multiple issue. So the CPU is going to examine the instruction stream and choose which instructions to issue each cycle. And then the compiler can help the CPU a little bit by still reordering instructions, but the CPU is going to resolve any hazards and anything that needs to be handled, like forwarding during runtime. So here is an example of static multiple issue. Oftentimes, we also call this very long instruction word. Well, the example is in the next slide, but here is an example of our multiple issue pipeline, right? So we have instruction fetch still, but rather than fetching one instruction, we have 1, 2, right? And rather than fetching one thing from the register file, I mean 2 things, we're fetching now 4 possible, right? And we have this ALU, and then we have this ALU. And now we have 2 inputs into memory as well. And coming back to the register file, we have 2 inputs to write back to the register file. But we have not completely duplicated our pipeline, right? The top pipeline can do some subset of instructions, and the bottom pipeline can do a different subset of instructions. So what can the top do? Do archive. What can it not do?
Anything that goes to memory.
It can't do load word, can't do store word. But what can the bottom do? Stuff with memory. It can only do these memory instructions, right? Or it also has assign extend immediates. Maybe it can do branching. Okay. So here is our example. So we're a two issue. So we can do on the top pipeline, our ALU or branch instruction. And then on the bottom pipeline, it's only doing load instruction. Okay. So let's see, why is this the case? It's because we only have this one for calculating branch target address. We have no other way for the bottom pipeline to reach PCA. So it is ALU or branch instruction for the top, load and store only for the bottom. So our instructions are not going to be 32 bits now. They're going to be two instructions appended together for 164 bits. Very long instruction word. Okay. And in the ideal case, our compiler will find for us an ALU or branch instruction along with a load or store instruction, and we'll fetch the bool. And then it will find another, fetch the bool, and find another pair, fetch the bool. And they can go in lockstep. But that is not always the case, right? We have these hazards, and because of, say, this dependency right here, they can't go together, right? So we're going to split this pair into two packets instead, which for our dual issue processor is like calling once. So here we can see an example. We have this loop. And for the first issue packets, it can only find the load word. There's no R type to go with it. And then for the second packet, it's doing this add immediate. There's no load word to go with it. Third packet, we have the add unsigned. No load word store word to go with it. Fourth packet can do the branch and the store word. So we're not doing much better than the single issue pipeline in this case, because we have lots of dependencies as well as our pipelines are not symmetrical. We have to have R type or branch on our top pipeline, and we have to have store word or load word in the bottom pipeline. So it's very restricted. But you don't have to have that as the case. Right? And often pipelines are symmetrical. We can fit many, many transistors on a CPU die. That's not a limitation anymore. All right. Another thing that is optimization that you may encounter is loop unrolling. So this is going to turn some for loop or something like that, rather than branching back, it's going to just copy paste all of the instructions. Because say we have this average of 4 to 7 instructions to execute between this pair of branches, then in the worst case, 20% of our instructions are just control. But if we know we're a for loop and we know that we're going to loop 10 times, rather than looping back 10 times, just copy paste the code, and now you never loop back, right? And you just improve your performance by 20%. So, right, here's our normal code. Here is its unrolled by 4. So rather than doing one thing at a time, I'm going to do 4 things at a time. Nice thing about loop unrolling is the compiler can do this for you. You can write the code like this because this is much easier to understand than this. So you don't have to worry about loop unrolling in this day and age. But the compiler cannot do everything. We are going to talk about in the next chapter, caching. The compiler cannot optimize for caching for you, unfortunately. You would have to optimize for caching yourself. And unfortunately, caching is probably the biggest performance impact that you can achieve by writing more optimized code for a given processor and its cache. So here's our unrolled example, right? We're going to fetch 4 things from memory. Add, store the results, and then we'll loop back, rather than do 1, 2, 3, 4 instructions, and then we have to loop back. Okay. So does loop unrolling make sense? Now with loop unrolling, if we have that multiple issue processor, look at how many more pairs that we can put together. So that's the other thing. We have dynamic multiple issue. Rather than the static multiple issue, like we're always fetching 2, right? Dynamic multiple issue, the CPU is going to decide whether to issue 0, 1, 2, however many it can support each cycle. And it's just going to make this decision based on avoiding these structural and data hazards. So this avoids the need for compiler scheduling, but it still may help to have compiler scheduling. And then the correctness of the code is ensured by the CPU compiler. So here is our example again. So we have all of these that we have fetched, and they're in our little buffers. And say we still have that to issue superscalar pipeline design, then the CPU can see I can't issue this load word with this add because they're dependent. But in my buffer, I have this sub that's going to come up, and it's independent. So combining this dynamic pipeline scheduling with out of order execution, I can find more independent instructions. So here, we're going to fetch a whole bunch of instructions. They're going to go into this buffer. They can then be executed in whatever order, as long as we maintain correctness, right? So if we can find independent instructions, they can go earlier than they are scheduled for, right? And then one of the other ways that we are maintaining correctness is, even though an instruction is done, we might want to commit them in order, so that, say we have an exception, then we didn't commit that instruction that's behind it, right? And it makes this restarting still possible. All right, so the other thing is speculation. So we already saw one type of speculation, right? Branch prediction is speculation. Am I going to be not taken or taken based on my, say, 2-bit predictor? I will guess one or the other. And then if I'm wrong, I need to correct it. If I'm right, then we're good to go. Everything that I've been doing is correct. So the other thing that we can speculate on is data. So we can speculate on loading data, right? So if I have code that is incrementing my index by 1, I can maybe presume that's the next time I see this function again, it's going to increment by 1 again, right? So rather than waiting for that to happen, I can load it right away, right? And if I'm wrong when I actually go to execute that instruction, then I just roll back, I flush everything I did, and then I go about with the correct data. So some concluding remarks on the data path and architecture. So the ISA is going to influence the design of the data path and the control, right? Pipelining is improving throughput using parallelism. So we have more instructions completed per second. That's our throughput. The latency for each instruction is not reduced. Because of the pipeline registers, it's actually increased slightly, right? So we are limited by structural, data, and control hazards that the pipeline handles. And then with multiple issue, dynamic scheduling, we can take advantage of this instruction level parallelism. So the dependencies are going to limit our achievable parallelism, but by combining all of those ideas together, right, with loop unrolling, with multiple issues, with out of order execution, I can find more instruction level parallelism than if I was only using one of those things, right? So this complexity, though, is what is going to lead to us hitting that power wall. Because in order to handle all of these exceptions, all of these dependencies, I have to have a lot of control logic. And in order to have, say, 20, 30 stages, I'm going to have a lot of registers. If I want 8-way issue, I've just multiplied my data path by 8 times, right? So that's what leads to this power wall. And our goal is to be right at that wall, right? If you want highest performance. So one thing to note is we did cover a simplified version, 5-stage pipeline. But I have now introduced you to these ideas that are improving upon that 5-stage pipeline. And you are going to learn about it and present them on the last week-ish of the course to teach us in more detail. Okay? And you can do that because pipelining in today's most advanced processor is not fundamentally different than what we discussed. It's just more complex. But the base knowledge, how it's done, all of that is the same. So you have all of the knowledge to learn more, and the final, like the project is the opportunity for you to learn more in your groups, and you'll also learn more if you pay attention to the presentations from the other groups. All right, so it is past time. You do have this reading and then these things over these from the slides.